Hi, I'm Dr. Bob Hogg, and in this video we're going to have a look at what might be called the other side of JASP, which makes it somewhat different from other statistical programs, which is the use of Bayesian analysis as well as what we might call classical statistical analysis. Now, if you've already had a play with JASP, then you might be aware that if you go and do something like a t-test, you are given a couple of options. You have got the classical analysis, which you would expect here, like independent samples t-test, paired samples t-test, or one sample t-test, but you're also given a Bayesian equivalent. In other words, Bayesian independent samples t-test, a Bayesian samples t-test, paired samples t-test, or a Bayesian one sample t-test. And it's exactly the same in all of the other options, for instance ANOVA, for instance, or regression. Now, what we want to have a look at today is what is the difference between this concept of Bayesian statistics and what we might term your classical statistics. So we do need to do a little bit of background to start off with, and so I've sort of put together some slides on this. We're not going to go into the details of where Bayesian analysis comes from. There are lots of videos and very good websites which will go into a lot of detail on that. It is quite a complex subject, but what I do want to do is to give you a very brief overview, then actually do a couple of experiments in this video and a second video where we will actually look at how we can implement Bayesian statistics in a very simple experimental way, which hopefully will give you a feeling for what it's doing when you run such an analysis in JASP. So if we have a look at the Bayesian analysis, then what I'm going to have a look at now is the difference between Bayesian and classical statistics in terms of some of the terminology you may be aware of, for instance, p-values, effect sizes, etc. Then we're going to look at the definition and the equation associated with Bayesian analysis, but again I won't go into the derivation of that equation. There, as I said, plenty of websites and videos about that. We're then going to look at the actual example, which is a Bayes box, what we call a Bayes box example, and then we're going to do a real-life simulation of that Bayes box to put it into practice, which will essentially be a live demonstration and will hopefully give you a much better appreciation of what Bayesian analysis is doing in practice. So if we have a look at these slides, then in terms of philosophy, you have got this classical frequentist analysis and also this Bayesian analysis. Now, again, if you've looked at my video on p-values, then you'll know that the classical or frequentist analysis is based on what we might call the long-run frequency of events. In other words, you're trying to estimate some particular statistic from a sample which is estimating what is essentially a parameter of a population. These parameters are effectively thought of as fixed, and essentially the data that we sample is the random element. And the inference is actually based on this repeated sampling and really gives us an indication of whether or not the differences we're getting between the statistic and the parameter is due to sampling error, or there's actually an effect that you're seeing. In terms of Bayesian analysis, it is slightly different. The probability is actually the true belief or uncertainty of what you're actually measuring. You're not using a sample, you're actually using actual data that you have. And so all Bayesian is telling you is how probable that is in terms of an effect. Because of this, essentially the parameters are essentially random variables. They're not fixed values. They're actually, being a random variable, or a distribution, a probability distribution. and we'll go into what that means in practice when we see the equation. But essentially this is moving from what we call a prior, which is what we believe to be the effect before we get any data, towards a posterior, which is what we get as we add more and more data. And so effectively the inference elements of this are updates of the prior beliefs about the data. So if we think about the concept of p-values, and this will obviously relate to the other video I've produced on this, you'll remember that the p-value is the probability of getting the data you have, or more extreme, under the null hypothesis. So essentially this is used to test this hypothesis, and effectively it's looking typically for a value of less than 0.05, or a 5% probability, which is the evidence against the null hypothesis. Now, one of the disadvantages of this classical methodology is that it doesn't actually give you a probability associated with the null hypothesis. You're just really proving that, or trying to look at a probability of whether or not the null hypothesis is actually the best explanation for your data, which is usually something like any effect that you're seeing is just down to sampling error. Now, in terms of Bayesian analysis, there are no p-values. In other words, you're essentially focusing on the effect and the probability of this particular effect that you're measuring given the amount of data that you have. You can do hypothesis testing, and this is usually in terms of what's called a Bayes factor, which in actual fact is a ratio between the probability of a particular hypothesis divided by the probability of the null hypothesis, or vice versa, depending on which way you're running the Bayes factor. So in actual fact, in Bayesian statistics, you are actually gathering information about the probability of the null hypothesis being correct, and hopefully we'll get to see that in the example. And so you are getting direct probability statements about all of the hypotheses if you have several. So again, one of the other things that you do have in classical statistics is effect sizes, and this is usually represented by Cohen's d, for instance, or an odds ratio, or Pearson's rho, for instance, and this estimates the magnitude of the effect. Now again, you get a certain amount of error associated with this particular value, and that is usually related to standard error, which of course is related to the amount of data that you've got, or essentially what your sampling methodology is. Now in Bayesian analysis, it's the effect size that you're actually measuring. So you are directly measuring an effect, even if you have a tiny amount of data. Now that means that you might get a very wide probability distribution of this particular effect. In other words, you have a certain degree of uncertainty about this effect because of lack of data. But as you add more and more data into the analysis, then essentially this distribution will narrow and will give you a much smaller range of values for your effect. And this can be measured using what's usually called the credible interval, which again can be any size you like, but again this can be made the equivalent of classical statistics, even though that's fairly irrelevant subject. So you can make that, for instance, 95% of the probability masses between two values of the effect. So how do you interpret your data when it comes down to these two different techniques? Well, essentially the results in the classical area is based on the statistical significance and also an effect size. And you find that if you're publishing, for instance, you will be expected to deliver a p-value as well as an effect size as well. Again, you do not get any direct probability statements about your hypotheses or your parameters. And essentially this parameter in Bayesian statistics is effectively now a probability distribution rather than a fixed value. So you are actually getting some sort of information about the probability of your hypotheses or your parameters. Therefore, giving a fixed value does not really make sense in Bayesian statistics. You can get a fixed value, you can get the median on this probability distribution, but again, this is somewhat nonsensical in terms of what Bayesian's actually doing in practice, and it's much better to demonstrate the effective distribution of this particular parameter. And what some people find is that it's actually more intuitive. So you can see there is a 95% probability that you have an effect, for example, because the effect is a probability distribution. So in summary, that the classical analysis techniques are based on p-values, confidence intervals, and effectively long-run frequencies. In other words, if you gather enough data, then you'll get closer and closer to the actual population size, and so your statistic will start to approach the actual value parameter of your population as the errors are reduced. And obviously this does give a disadvantage with this technique, is that as you get more and more data, effectively you'll always get a p-value less than 0.05 because essentially the standard error will become so small. In Bayesian analysis, you are focusing on what's called posterior probabilities. In other words, the probability distribution of the effect. You get credible intervals, and what you're doing is you're constantly updating your beliefs, and that will actually be the focus of our little experiment, which we'll get to shortly. So essentially, Bayesian provides these direct probability statements, and classical statistics do not. One of the main issues with Bayesian analysis is it's highly computational. It takes a lot of computational data to do any sort of detailed analysis, and as such it's only been used more recently because of the advent of extra computing power within normal desktop devices. So when we come down to Bayes' theorem itself, what you find is you'll see this particular equation, which again, I'm not going to tell you how this is devised, but effectively it is saying that you have got the probability of the hypothesis is true, for instance. In other words, this is the posterior distribution. All these terms are distributions and are not fixed values. And that is made up of a number of components. The first one being what we call the prior, which is usually some information we have about the effect before we gather any data. Now, you might have a lot of information based on previous experiments or previous work, and so this could be a fairly accurate representation of your particular problem. Or it may be that you have very little information, in which case you might have what we'll call an uninformed prior. In other words, very little information, and lots of the options you could get within that would be equally probabilistic. And this is what we're going to do in our example. This is then updated by multiplying by what we call the likelihood, and this is effectively based on the data we have started to gather, and these two are multiplied together to effectively get this posterior. But because of this multiplication, whereas the likelihood function and the prior function are actual true probability distributions, once you multiply them together, then they cease to become a true probability distribution because they don't have the range 0 to 1. Therefore, we have to, in effect, put in an initial factor to reduce that to a true probability distribution. In other words, this particular normalizing factor here. Then what we do is effectively we get what then is in effect the posterior distribution, which is a true probability distribution, and we feed that back in the next time we gather some more data, and this becomes the prior, Our new data then becomes the likelihood function, it gets normalized and it gets fed back, and we have this cycle that we're going through. And again, I'm hoping to demonstrate that in our actual experiment. So what's our experiment actually going to be? Well, this is the detail of the experiment, and I'm going to run through the first stage just in the slides, and then we're actually going to do it for real with a spreadsheet which I've set up to run this a number of times. So we're actually going to have a bag of dice, and just to show you that we actually have it, here is the bag of dice here, and inside that bag of dice I have 6 different side dices. And as you can see from the slide, we have a 4-sided, a 6-sided, an 8-sided, 10, 12 and 20-sided dice, and these are the possible hypotheses we're going to have in our experiment. In other words, I'm going to put them back into the bag, and I'm going to pick one at random, and I won't tell you what it is, and then I'm going to just gather some data about that particular dice to try to find out which particular dice I've picked up, just simply by using Bayesian analysis. In other words, the data is going to be the number that I actually roll on the dice, and using that data I'm hoping that it will identify the probability of which particular dice it is in practice, if the experiment works how I hope it to work. So what I'm actually doing is I'm going to select at random one of those dice and run the experiment. Now, how are we going to run this experiment? Well, we're going to use what we call a Bayes box, and this basically simulates the process. So what we've got is we've got our hypotheses here. Now we've got essentially 6 hypotheses based on which particular dice we've got. If we want the null hypothesis, that's just the probability of it not being a 4-sided dice or not being a 6-sided dice, etc. So the first thing we have to do is to decide on our prior, which, remember, is the information we have before we gather any data. And I've not gathered any data yet. I've not rolled the dice, although I have selected it. So what are we going to do? Well, we know that there are 6 dice in the bag. I've just showed you that. So the prior essentially should reflect the fact that I can pick any one of those 6 dice. And it is just a simple random choice out of a very dark bag. That means the probability would be the same for all of them. In other words, 1/6. Now, just to put this in context, if you're getting confused already, if, for example, I decided that I had a number of dice and I would just put them all in the bag, and in effect I found that I had more normal, what you might call normal 6-sided dice, and I put 4 of those in the bag but 1 everywhere else, tell you what, we'll put 5 of those in and 1 everywhere else, then I would effectively have 10 dice in the bag, and it would be 0.1 here. We would have the 5 6-sided dice, which would be 0.5, 0.1, 0.1, 0.1, 0.1. That would be an informed prior, because I knew I didn't have an equal number of the different types of dice in the bag. So what does that mean? Well, it means that the prior, in this particular case, because there are an equal number of dice of each size, will be 1/6, which is 0.1667. So let's actually, before we do the real experiment, let's just do a simulation to see how this Bayes box works. So let's say I roll a 6. Well, then we need to generate what we've called the likelihood function. Now, if you think about this logically, then we've got H1, which is a 4-sided dice. The likelihood of rolling a 6 on a 4-sided dice is actually 0 because it only has the numbers 1 to 4, so that becomes a 0. In terms of a 6-sided dice, the chances of rolling a 6 are 1 in 6. The chances of rolling a 6 on an 8-sided are 1 in 8. The chances of rolling on a 10-sided dice, 1 in 10, 1 in 12, and 1 in 20. In other words, that is our likelihood function, which describes what is likely to happen. So in that particular case, you can see I've got 0, 0.1667, 0.125, 0.1, 0.0833, and 0.05. And that is our likelihood function. Now what we now need to do is to multiply the prior by the likelihood, as in Bayes' equation, which gives us this value. Now you notice so far we've got a probability distribution here, and the posterior has to end up as a probability distribution here. What is going to happen as we move through, you'll see that we multiply these together, and because of that we now don't have a true probability distribution, because the sum of these probabilities is not 1, it's 0.0875. Therefore, to normalize that to a true probability distribution, we have to take each of these values and divide it by 0.0875, which gives us all these particular values here, which in turn add up to 1.0. And what does that actually mean? Well, it actually means that so far we've actually got now some probabilities for each of our hypotheses. And here they are. You can see that at the moment, based on this very, very simple one piece of data, we know that our H1 probability is 0 because we rolled a 6, and there isn't a 6 on a 4-sided dice. On a 6-sided dice, the probability is 0.3177, 8-sided 0.2377, and so forth and so on. So at the moment, the probability distribution is telling us that we certainly haven't got a 4-sided dice, and the most likely dice we've got is a 6-sided dice. But that's only with one small piece of data. Now remember, I said that one of the advantages of Bayesian statistics is that you do get information on the null hypothesis, and the null hypothesis is that it is not a 6-sided dice, and that's simply 1 minus the 0.3177. So we do get information on the null hypothesis as well as our particular hypothesis that we've got. So in this particular case, if we do that, we can calculate this Bayes factor, which is these particular values here, which is the ratio between the actual hypothesis and the null hypothesis, or the other way around. And so you can see here that in terms of the Bayes factor, which is that this hypothesis is true, which is 0.4656, which is greater than any of the others. But of course it's still quite small because we've only had one piece of data. And that is basically how Bayesian analysis works. So let's do an actual real experiment. And what I've done is I've set up this particular spreadsheet to do that. It's got no data in it at the moment, so just ignore everything you've got. So I am going to actually roll a dice, and if you listen carefully you will actually hear the dice roll, but I'm not going to show you it for now. And in actual fact I've rolled a 2, so I'm going to put 2 into here, and you will then get an update of the probability distributions here, and the update of the Bayes factors. Here are the priors, here are the likelihoods, and you can see here that unlike the 6, of course, is the 2 is available on each of the dice, and so we do have all of the probabilities exist within all of the different hypotheses, and you can see the probability distribution here in this particular graph, and the current Bayes factor are these values here, which says the most probable hypothesis is actually the 4-sided dice. Okay, we need some more information, so let's roll the dice again. And now I've rolled an 11. So I'll just put 11 into there. And you can see immediately what's happened is now, of course, by rolling the 11, is that suddenly the 4, the 6, the 8 and the 10 are impossible. And so all of the probability mass has now moved after this piece of data into the 12 and the 20 area. And you can see how this has happened. In other words, we've got the posterior after the first roll that's been moved into the prior. We've got the data, which gives us the likelihood, and we multiplied them together, normalized. Here are the values, and you can see now when we come to the Bayes factor, then we've got 2.7778 and 0.3600, and of course these values are 0, which obviously makes the inverse Bayes factor infinite. We'll roll another, and this time it's rolled a 10. And you can see it's been updated slightly, and again we're getting a strong probability that it's a 12-sided dice as opposed to a 20-sided dice, and using the same methodology. And finally I'll roll the dice again, and as I say, with this being an actual real experiment, can't control the data, but there is the final probability distributions after we roll this particular 8. So you can see now our probability distribution is that we have a very high probability that, in other words, an 88% chance that it's a 12-sided dice, and we have about a 12% chance that it is a 20-sided dice. And just to show that I'm not cheating, there is the dice that I've been rolling. And it is in fact the 12-sided dice. I'll be quite glad that our experiments worked in practice. But what I've been hoping to show you here is the mechanism by which Bayesian analysis works. In other words, you start off at the beginning of this process with some prior knowledge, and in this particular case it is not a great deal of prior knowledge. We just know that it could be any one of 6 different dice. We've then got a likelihood function based on the first roll of the dice that's in effect multiplied them together, and once normalized give you the posterior distribution where we are so far with the data we have. This is then moved into the prior for the next cycle, because that's the information we have. We have more data, the likelihood is updated, essentially the multiplication is updated, and the posterior is updated, which then carries on to be the next prior, and so forth and so on. And this is essentially what JASP is going to be doing, and what I will be showing you in the next video is that is what it does in practice. And so hopefully I will show you, using some of the facilities within JASP, that is exactly what it is doing when it does in effect a Bayesian analysis.